We're going to talk about positive and negative numbers and what they look like in binary. But first, let's review the rules of binary addition. Addition's pretty straightforward. 0 plus 0 is 0, just as you would expect. 0 plus 1 is 1. 1 plus 0, same thing. Remember, addition is associative. You can switch the order. It doesn't matter if you add x plus y or y plus x. So 1 plus 0 is also 1. The exception to the rule here is 1 plus 1 is equal to 0, and we carry the 1. This would be like in decimal. If you add 5 plus 5, you get 10, but you write down a 0 in that column and you carry the 1. Same thing with 1 plus 1. We can't write a 2 in that column. We can't write a 1, 0, because that's 2 digits in the column. So we put the 0 in the column and we carry the 1 to the next column. So let's add 3 plus 1 in binary. We know we're going to get 4. So in binary we know we're going to get 4 zeros, a 0, 1, and a 0, 0, because 3 plus 1 is 4. What actually happens here is the last column on the right hand side, the least significant column, 1 plus 1 is a 0, and then we carry the 1. We carry the 1. The carried 1 in green plus the yellow 1 is also a 0. We write down a 0 in the second column. We carry the 1, and the third column becomes a 1, which represents the binary 4. Now, let's look at binary subtraction and review these rules. 0 minus 0 is 0. 0 minus 1 is a 0, but we have to borrow the 1 to literally make that 0 a borrowed 1, almost like a 2. And then 1 minus 0 is 1, 1 minus 1 is 0. So those rules are pretty straightforward except for borrowing. So now let's subtract a decimal 4 from a decimal 3 in binary, and we should get a minus 1. And let's see what happens. And if we follow these rules, we will be borrowing 1s all the way to the left. And we will get 8 1s, or 255. But we know the answer is negative 1. So is it 255 or is it negative 1? It's almost like we have an infinite borrowing going on to the left. What if you subtracted 1 from 0 in decimal? Would you get 9999999? The answer is it's subject to different interpretation. This is why computer languages have signed and unsigned keywords, because this allows us to specify how that byte or integer will be used, how it will be converted to decimal, how it will be displayed, what its value is internally. But this seems rather confusing, doesn't it? Well, languages like C and C++ and C#, they support signed and unsigned data types. But Java only has signed integers, except for the character data type, which is an unsigned short. Now, James Gosselin developed Java in 1991, and he thought that signed and unsigned types were too confusing. And he was right, because in C and C++ and C#, even well-seasoned programmers make mistakes and use the wrong signed or unsigned data type, or don't think through what the magnitude or values are of all the numbers in their formula. Together we're going to unravel this confusion and explore how signed and unsigned data types work. So what is a byte overflow? Well, it means that a byte can only handle a maximum value of 255, and if you add 1 to that 255, it would carry the 1 into the second byte that does not exist because it's a 1-byte number. So if you look at the yellow 8 1s and we add a 1 to it, we get the green 0s. That byte becomes 0. But the byte to the left, that arrow on the left, shows where that red 1 carry would be in the least significant bit of the second byte. So that byte of green values of 0 has overflowed. So what is a byte underflow? Well, it means if you have 0 in your byte and you subtract 1, you would borrow 1 from the second byte, again, that does not exist. So your byte in green would go all to 1s. It would underflow from 0 back to the highest number of 255. And the second byte, where the arrow shows in red, would be all ones. So in that case, we're trying to put a value that is too big, takes too many bits, takes more than 8 bits to store in a byte. So what is the range of a signed byte? A signed byte can go from 0 through 127. And you can see the green bits. 0 is obvious, and 127 is just the 7 least significant bits all set. That has to be 127 because we know the most significant bit has a value of 2 to the 7th power. We know that the value is 127 because the most significant bit has a value of 128, and this is 1 less than that. So then what about negative numbers? If you're assigned byte, you can only have a positive number of 127. We lost half of our values already. We can't have a value of 128 to 255 like an unsigned byte could. So the signed byte has a value of -1, as we just seen from the other slides, of 111111. So the signed byte has a value from -1, which is 8 ones. It would be 255 if it was unsigned, but we're treating the byte as signed. So in that case, it's not 255, but it's -1 because it underflowed below 0. And then the positive number, and then the maximum negative number we can have is -128, which looks a lot like positive 128. We'll get to that in a minute. But just remember that there is no minus sign or plus sign like there is in decimal numbers. That's all formatting. Whether you print your number out with a negative sign or a positive sign or a dollar sign, or you print negative numbers in red or positive numbers in green, that's cosmetic formatting and has nothing to do with how the bits are stored internally. So you can tell a number if it's positive or negative by looking at the most significant bit. Positive numbers will always have the most significant bit, 0. And negative numbers will always have the most significant bit as a 1. So that's an important takeaway to note. Well, here's a memory peg that you should know, that 2's complement was discovered in 1958. That's amazing by itself. The second amazing thing is there's a rule to convert to and from signed and unsigned, and it's this: invert the bits and then add 1. It's that simple. You should remember this. Invert the bits. All the 1s become 0s and all the 0s become 1s. That's inverting the bits. And then you add 1 to that number. And that'll convert you from positive to negative numbers. Let's see how this works. We're going to look at the numbers in red. We have 0. We're going to invert all the bits, and we're going to get all 1s. We're going to add 1, and it's going to overflow back to 0. So in the bottom yellow, we proved that 0 becomes 0. A 0 negative number and a 0 positive number are equal, which is what you'd expect. If you think of a number line, there is 1 0 in the middle of the number line that divides the negative and positive numbers. Now let's take a -1, invert all the bits. It becomes 0, and add 1, and we get a positive 1. So -1 becomes a positive 1. We just proved that FF in hex, or 11111111, 8 1s go to a 0, add a 1, and become a single 1. So -1 and positive 1. That's the conversion. And then you can do it back. You can take the positive 1, and you can flip all the bits, add 1, and you can get your FF back or a negative 1. It works both ways. Let's try the number 3. So on the left, we have the red 1, 1. We flip the bits, add 1, and we get a negative 3. Now if you would count in place and look where that number falls, you would see that it would fall in the correct slot or position after the negative 1, negative 2, negative 3. And then likewise we can convert a negative 3 back into a positive 3 by doing the same simple invert the bits and add 1. This always works. But here is something to think about. Let's take the negative 128, which is 1 followed by 7 zeros, invert it, we get 127, we add 1 and we get 128. But you're saying, wait a minute, we wound up with the same number. It's kind of like 0 and 0. No, because the numbers, the red numbers on the left, are treated as signed bytes. After the equal sign on the right hand side, those are treated as unsigned bytes. So we're showing that a negative 128 on the left as a signed byte is equal to 128, or converted to 128 as a unsigned byte. Something to think about. So the answer when you convert to unsigned, you have to treat that byte as unsigned. When you convert the positive to the negative, you have to treat the resulting byte as signed. We already talked about unsigned shifting. Unsigned shifting is sometimes called logical shifting because you push a 0 in from the most significant bit and all the bits move to the right and the right bit falls off and is discarded. Or you push a 0 in from the least significant bit and the most significant bit is discarded. There's nothing special about unsigned shift or logical shifting as they call it. But signed shifting is special. Signed shifting has to preserve the most significant bit. So as the bits in this case move to the right, they're shifted to the right. This is sometimes called arithmetic shifting. Bit 7 has to be preserved and remain the same. Bit 7 is copied also to bit 6, and bit 6 moves down to bit 5, and so forth, and bit 0 is discarded. The same thing with shifting to the left. You shift to the left, but you have to make sure that when you're shifting that bit 6 is cleared, because if bit 6 is a 1, you'll shift and you'll overflow your positive 127 of the maximum value, because you'll be shifting 64, which is bit 6, set to a 1. So make sure the magnitude of the numbers are within range when you shift. In all these examples, I used a byte as a signed and unsigned number, but it's not bit 7 that was important. It's the most significant bit. That's your signed bit. Signed numbers come in any size you can imagine. Doesn't matter if it's 8, 10, 12, 13, 16, or 20 bits. As long as you treat the most significant bit as the special case signed bit, the 2's complement will work.